The broadcast is now starting. All attendees are in listen-only mode.
Okay, well, welcome everybody to the IEAGHG webinar for today, which is on reducing water usage in power plants with carbon capture and storage. And it's actually based upon a new study of ours, which is around the costs of reducing water usage. And today we'll have presentations from Monica Garcia from IEAGHG, from Regina Sander, and from Paul Feron from CSIRO Energy in Australia. Next slide, Monica. And before we start, I just need to show you this disclaimer to show that we're a technology collaboration program of the IEA, International Energy Agency. We're organized under the auspices of the IEA, but we're not part of them. We're autonomous from them. So anything we say doesn't represent their views. Next slide, please. And this is who we are. Our full name is the IEA Greenhouse Gas R&D Program, set up in 1991 by the IEA. We have our 36 members from 22 countries, and we're a technical-based information organization. We don't do policy prescription or advocacy for any particular technology. Next slide, please. And I think you're probably all familiar with the activities of IEAGHG. We produce our technical studies, of which this is the latest one you'll hear today. We have our international research networks, our GHGT conferences, our post-combustion capture conferences, and our international CCS summer schools with over 600 alumni now, and hopefully going to Indonesia this year. Next slide, please. And our main conference, the GHGT 15 conference, you may be aware that we've had to postpone the date of this because of COVID-19. That was a hard decision, but working with our great hosts, Khalifa University, we felt it necessary to safeguard the attendees and participants. And also, we will now stick to those dates, whatever. So those are the new dates, 15th to the 18th of March in 2021, and the technical programs in place. Next slide, please. So with our technical work and our reports, what's really important to us is that they get used appropriately. So we are active in getting these used in different regulatory and policy fora around the world. In particular, at the UNFCCC COPs, where we've been organizing the main CCS side event, and also with the IPCC, the Intergovernmental Panel on Climate Change, where we're expert reviewers and observers to that. And by working in those two environments in particular, we do get exposed to a range of views on CCS. We work with environmental NGOs, we're engaged with those, and again, they have a spectrum of views themselves as well. That does let us know, what concerns they have, what sensitivities there may be. And the work that we're going to be presenting to you today really was prompted by a report from Greenpeace in 2008 that expressed concern about water consumption going up by up to 90% increase with post-combustion capture plants on fossil power stations. And this got quite a lot of attention at the time, and it prompted us to investigate for ourselves the issues around water consumption with capture plants. And that started a series of reports and work that we've done to look at it from a more balanced perspective. And that's very important now because we are engaged with the IPCC as expert reviewers. Next slide, please. It's more important now than it was even then. Obviously, any environmental interaction with CCS is important, but with water consumption now, it's one of the 17 Sustainable Development Goals. It's SDG 6. And this is now used by the IPCC in the evaluation of the mitigation options. They use these extensively in the IPCC 1.5 report, special report in 2018. And as peer reviewers, it's our job to make sure they have the right information that's available from the literature. And so thanks to the work that we've produced in our reports and our papers, and also the GCCSI paper with the SDG 6 on access to clean water and water use efficiency. We were able to balance out some of the negative literature with some of the more neutral literature to give it a more neutral scoring in this SDG system that's been used by the IPCC, and that continues now under the IPCC in AR6 as well. So these reports and papers are very important for us to use, and the latest one will be continuing that theme. Next slide, please. And we do all the things we do. Thank you very much to our 36 members, and that's just a slide to acknowledge them and their flags and their locations all around the world. Next slide, please. So the webinar today will be essentially in two parts. Monica Garcia is going to present the background work from the IEAGHG on this topic, and also some of the work from the International CCS Knowledge Centre in Canada. And then the meat of the webinar is going to be from Regina Sander and Paul Feron at CSIRO on this new study on understanding the costs of reducing water usage in power plants with CCS. Now, on your control panel, you should have a question sub-panel within that. Please write in your questions as we go through, and at the end of this webinar, we'll have some time for the presenters to answer your questions. Next slide, please. So we will be making this available afterwards as well as a recording for those in different time zones who could not get through. So the presenters today, Monica Garcia Ortega from IEAGHG, who's our Senior Technology Analyst, focusing on CCS in industry and also emerging capture technologies and on hydrogen. Next slide, please. And we have Regina Sander from CSIRO in Melbourne, who is the research engineer there. Next slide, please. And we have Paul Feron, who is a science leader in CSIRO Energy, and he's been their post-combustion capture program lead since 2007. That's all I wanted to say, so I'll now hand over to Monica to present the background. Thank you.
Okay. Yeah, thank you very much. As Tim mentioned, I'm gonna present the background and the motivation of this IEAGG study that we are gonna deliver soon this year. So I'm gonna give you an overview of our activities since 2010. So first, just to explain you a bit more why we wanted to study this water consumption and energy consumption in the power plants and how those are connected is because energy production consumes a significant amount of water, and equally providing water demands energy. So the Water-Energy-Nexus defines the relationship between energy and water to ensure the availability of both resources. So what we saw is the power generation can impact water resources, and increased energy demand is projected in the coming years. So we also expect the water consumption to increase in the coming years. So we have explored the implementation of CO2 capture systems in power plants, and water availability has been identified as one of the parameters to consider when designing CCS systems in power plants. So basically, the questions we made to ourselves when we started exploring this area is what about the techno-economics, what about the challenges, and about what about the different regions. So about the techno-economics, we have seen that the region has an impact on the economics, and also the challenges. We wanted to explore not only the techno-economics, but also policies, because depending also on the regions, we are going to have different policies related to water consumption. And different regions also are going to impact on the ambient conditions, and also the storage sites available around the power plant, and also other factors that are going to impact on the design of the power plant. So with that, we started in 2010, and we delivered this report in 2011. This report was titled Evaluation and Analysis of Water Usage of Power Plants with CO2 Capture. And this study is focusing on the water consumption of power plants with and without CCS. So as I mentioned, power plants required a significant amount of water, also required raw fresh water for boiler feed water makeup, flue gas scrubbing, amongst other areas within the power plant. So one of the things we identified is that cooling water is required, and that has also an important impact on the water consumption in the power plant, and cooling system will have to be designed accordingly. So if water availability is a concern, we want to explore also which techniques are available that could be used to reduce the water usage in power plants and power plants with CCS. So in this study, we have explored different techniques to reduce water consumption, such as air cooling, wastewater treatment, water recovery from flue gas, rainwater utilization, water recovery from lignite drying, dry bottom ash removal systems, the use of catalysts to decrease the steam consumption, saturator-desaturator system to provide steam, using nitrogen instead of steam, water recovery from gasifier slag removal, and use of nitrogen from an air separation unit as a coolant. We explored those options, and we went further in the first three: air cooling, wastewater treatment, and water recovery from flue gas. So main conclusions we have from this study in 2011 is that adding a CO2 capture system might increase water requirements, but there are techniques to reduce the water requirement to zero or close to zero. So this might increase is related to it will depend on the type of power plant and also on the design of the power plant. So based on that, the water requirement is not expected to be a constraint to adopt CO2 capture technologies. But also we have to take into account that water consumption reduction strategies will reduce the thermal efficiency if we compare with the base case scenario where we are using water cooling plants and we are not implementing any strategy to reduce water consumption. So that can impact in the cost of electricity. And in this report, in the cases we explored, we estimated that between 12 and 13%, although we wanted to also study that further. So with that, we considered that this is not a deterrent to adopt CCS. And as I mentioned, we explored the consumption of water in power plants and power plants with CCS. In the study of 2020 that we are going to deliver soon, we have explored two areas. One is the power plant and one is the storage site. So focusing in the power plant and also supported by our study in 2011, we wanted also to explore different developments that have been delivered or different cases that have been studied over the years. And I wanted to highlight this study from 2019. The title is Heat Rejection Design for Zero Liquid Discharge Shunt Coal-Fired Power Station Integrated with CO2 Capture and Storage. And that is an example of how a design can integrate a CCS system and also strategies to reduce water consumption in the power plant. So the study was a collaborative effort between MHI, MHPS, and the International CCS Knowledge Center, and they explored the implementation of this strategy to reduce water consumption in a power plant which has 305 megawatts gross output. And this power plant also is a promising candidate because of its location. It's close to potential storage site where EOR can be implemented. It is also close to the boundary dam, and also because of its size, it was a promising candidate to study it further. So what the other authors did, they studied hybrid heat rejection system based on a dry cooler and a wet cooler. That maintains a neutral liquid impact while adding SO2 and CO2 capture processes. And the water produced by the capture process is utilized as the primary source for wet cooling. And it's also important to mention that it's maintaining zero liquid discharge status, because that is also significant in some regions, depending on the policies. So this is a graph also from their study. And I wanted also to mention that the heat rejection was designed to be able to shift the cooling load between dry and wet cooling in response to variations in dry and wet bulb temperatures. And the research on the temperature variation through the year showed that the annual average of heat rejection load shift toward the wet cooling system because of the lower temperature and the water availability from the CO2 capture process. So we have to take into account that this results in reduced farm power requirements also. But from this study, I would like also to highlight that they designed a hybrid reaction system that can solve the challenge of integrating CCS in an existing facility with limited water availability, and also considering the zero liquid discharge regulations. So as main conclusion from this study is that water availability is not a constraint, and a proper design can solve this challenge. So as I mentioned, we explored 2 areas over the years. One is the power plant, and the other one will be the storage site. So we delivered this study in 2012. The title is Extraction of Water Formation Water from CO2 Storage. And we wanted to explore the extraction of saline water from storage formations, and because that provides a solution to pressure management. It can also has some other benefits. And we wanted also to explore what we can do with the water if the water is actually used or if it is disposed. So this study explored the potential of using the water extracted, also using a treatment in several applications. And also we have to consider that there are like a range of geological conditions, ambient conditions, and also formation water quality. So based on that, we explore different regions. And the case of studies were based in Germany, Canada, Australia, and USA. So from this report, we extracted that the reuse of water extracted after treatment can be explored as an option. So we studied that further, and we saw that in some cases, the cost of treating the extracted water is less than the standard base rate of water in this specific area. So there is a potential to use this water, and some uses that we explore was to use it as a potable or agricultural water supply. In other cases, the preferred option was disposal, rejection into geological formation. So we also saw that the further techno-economic analysis was recommended, also to explore both areas, capture and storage together. So the key messages that we can extract from the reports is that there are available techniques to reduce water consumption in power plants with and without CCS, and that the location plays an important role in the economics and technical challenges. So that provides us the motivation actually for the report that we are going to deliver soon this year, because we wanted to explore a more in-depth European evaluation of the costs and benefits of integrating water usage with CCS that explores the increasing water consumption resulting from CO2 capture. We wanted to study further the techno-economic and regional factors influencing potential reuse of extracted water from the storage site and the need to achieve the quality specifications for the water. Also, we have to consider the value of adding a CO2 capture system to the power plant, and regarding the global ambitions to cut CO2 emissions. So we wanted to evaluate the influence also of the location on the Water-Energy-CCS nexus in these different regions. So with that, I want to show you also the references used for that presentation, and then I think my colleagues from CSIRO will continue the presentation, introducing you the study to be delivered in the coming months. Thank you very much.
Sorry, just making sure. Can you see my slides?
Yes.
Yes, we can.
Okay, excellent. Just want to confirm before I start talking. So thank you very much for the introduction, Tim and Monica. Paul and myself will be presenting some of the findings of this study titled Understanding the Cost of Reducing Water Usage in Coal and Gas-Fired Power Plants with CCS.
Regina, they're in the normal PowerPoint at the moment. They're not in slideshow.
So we are on the wrong screen. Yeah. Okay. I need this would happen. Could you take me out again and I do it back? Because I just selected the wrong screen.
Okay, it's still on the conventional PowerPoint display.
Oh yeah, if you can you just cut me off? That's what I mean.
Just
take this screen share away from me, and then I can select the screen again.
Oh,
yeah,
okay, Suzanne, can you do that, please?
just bear with me.
Because I can't find it now. Apologies.
I'm just switching back to Monica for a second.
Sorry, Monica.
Are you ready for it, Regina, to come back?
Yes, yes. Yes, that should be it.
Yeah,
That's
perfect.
it.
Yes, yeah, sorry, I just clicked.
Right.
Anyway, we'll just start. Yes, so the title of our study is Understanding the Cost of Reducing Water Usage in Coal and Gas-Fired Power Plants with CCS. So I'd like to start by acknowledging the other researchers that contributed to this study from the University of Sydney, CSIRO Energy and CSIRO Mineral Resources, North China Electric Power University, and of course, Monica Garcia and James Craig from the IEAGHG. I'd like to start with a brief introduction into what we've actually been doing and then the objective of this presentation. We'll be looking at 2 case studies that investigate the cost of reducing water consumption in thermal power stations with carbon capture and storage by 2 different means. That's why 2 case studies. We also provide briefly an indication of the conditions that encourage the use of formation water extracted for the purpose of CO2 storage, and then finish with the conclusions. So just indicated, we'll be looking at 2 different case studies, investigating 2 means of how to reduce freshwater consumption at a power station with capture. So in the first case study that Paul will be presenting, we will reduce the water consumption at the power station with capture directly through the application of different cooling systems. And this case study is set in the Netherlands. In the second case study, we look at using formation water that's extracted for the purpose of CO2 storage and treat it and use it in the power station with capture. And here we look at the effect of location. And therefore, this study is set in the Netherlands, China, South Africa, India, and Australia. The objective of this presentation today is to highlight the water demand of the power station resulting from CO2 capture and the associated cost of reducing this demand. We're also trying to provide an improved understanding of the economics of utilizing the formation water that's treated in the power station and indicate the conditions under which this may present a viable option. So we'd now be starting with the first case study that looks at the water consumption at power stations with capture, applying different cooling systems set in the Netherlands. And I would be handing over to Paul now to present the next slides.
Okay, thank you, Regina, and good day to you all. I hope you're all safe. I'd like to go through some of the results of our study when it comes to power plant modeling, including the capture part of it. And the location of the Netherlands has often been chosen in many IEAGHG studies as a location, and that's very handy for comparison reasons. So we looked at 2 different types of power stations, one coal-fired power station using ultra-supercritical steam conditions, and the other one natural gas-fired combined cycle where the gas is supplied via pipeline. The steam conditions were typically around 295 bar for the coal-fired power station, 600 degrees C. We used a single reheat, and for the NGCC it consisted of 2 gas turbines and 1 heat recovery steam generator. We looked at these two cooling systems, evaporative cooling and air cooling. We also looked at once-through cooling. We're not going to talk about that today, but it will be in the report that is coming out soon. When it comes to the capture plant, we integrated that fully with the power plant for both the coal-fired and gas-fired power stations by extracting steam, and that steam then went for liquid absorbent regeneration in the capture plant. And the capture plant, as it says, was based on chemical absorption technology, and we chose an amine process that we defined in an earlier study as being reflective of what's currently around globally from commercial vendors. It consisted of a 40% amine solution, tryptosine A and P, in a 1:2 molar ratio, and we found that using that particular absorption liquid together with a particular process design based on intercooling and rich split, we were able to get to the performances that you might find in sort of state-of-the-art power station for CO2 capture. So the reported duty for the coal-fired power station flue gas would be 2.5 gigajoules per ton. For the gas-fired power station is around 3 gigajoules per ton, which is what we found to be typical for the state-of-the-art power plants with capture. So what you see in this slide is just the gross power output and net power output. So when you go from evaporative cooling to air cooling, you will see that there's a difference in the gross power output, and that's simply because the condenser conditions are different. For the conditions in the Netherlands, air cooling gives you a condenser temperature of 34 degrees, and for evaporative cooling it will be around 28 degrees. And that already gives you a reduction in gross power output if you go to air cooling. We looked at a number of situations there. So for the capture system, you can use evaporative cooling and you can use air cooling as the power plants are, but you can also have this hybrid combination of evaporative cooling for the power plant and air cooling for the capture plant, and that proved to be quite interesting option for reducing water consumption. Next slide, please, Regina. This slide shows you a little bit of the efficiencies that we ended up with for the plants with capture and without capture. So the light bars, pinkish bars, are the coal-fired power stations, and the blue bars are the natural gas-fired combined cycles. So we ended up with typical efficiencies without capture of around 44.4% for the coal-fired power stations, and around just over 58% for the natural gas-fired combined cycle, which is representative of what you could find nowadays in the power sector. As you see, obviously, when you then attach a PCC plant to the coal-fired power station and the natural gas-fired combined cycle, it will lead to a reduction in output. The graph in the right-hand corner shows you that that reduction is between 7 and 8% across the board for all of these power stations. But the air-cooled power station already starts off with a lower efficiencies because of that lower condenser temperature, but also there's quite a bit of electricity going into the fans, and that we need for the air cooling system, and that gives you typically an efficiency hit of between 1 and 2% evaporative cooling compared to air cooling. So that's something that we need to bear in mind, because that also will translate into the plants with CO2 capture. What we could see there also is that we can attach air cooling. This is the EVPCC AC option to a power plant with evaporative cooling, and that gave us a little bit of a lower efficiency in all cases, but not by much compared to a totally evaporatively cooled power plant with CO2 capture, and that was an interesting result of this study. Next slide, please. Here we look further into the water consumption of these power plants. So if you have a coal-fired power station, the water consumption comes from obviously cooling, but it also comes from the FGD that is needing water, and some other systems as well in a coal-fired power station. For gas-fired power station, that cooling requirement is obviously less, bearing in mind that we have about the same gross power output. If we then take an evaporative cool power station and add PCC onto it, that is also getting its cooling from evaporative in an evaporative way, you see quite a drastic increase in water consumption. It's around 25% for the coal-fired power station, and percentage-wise, it's more than 30% for the gas-fired combined cycle, which is significant. But if we, instead of using that evaporative cooling for the capture plant, use air cooling, we can actually reduce that additional power requirement to negative values. So we actually have a lower water consumption for the option where we have the power plant evaporative cooled and the capture plant air cooled. And that's quite an important finding, because there's no need to assume that if you add PCC to a power plant, that you immediately end up with a higher water consumption if that capture plant is then air cooled. As you can see, obviously, the top graph on the right-hand side, the air-cooled versions have very low water demand, water requirement. It's just for makeup, boiler, feed water makeup, and in the coal-fired options, you also have the FGT that requires water. If you look on the right-hand, really the right-hand side of the first graph, there's a little blue bar that indicates a water requirement for the NGCC as well, for air cooling, and that's coming off things like the makeup for the amine solution, but also you need to cool down the flue gas to temperatures that are suitable for the capture process, and that leads to a water requirement as well. But as you can see, it's quite minimal. So air cooling actually reduces the overall water consumption compared to the power station without capture. That's an important finding. But the next question, and that's answered in the next slide, is at what cost, obviously. So this slide shows you the levelized cost of electricity is in euros per megawatt hour. We are in Europe after all, for the various cases that I showed you already before. And what you see, if you go from left and right on this graph, you go from evaporative cooling to evaporative cooling with post-combustion capture, you see a significant cost increase. If you then go to the option with air cooling, you see that the cost will increase further, because it's quite capital intensive to install air-cooled condensers, but not by much. So it is an increase, but on average is around 5.3 to 5.4% for the capture plant in the case it uses air cooling instead of evaporative cooling. And that is a cost increase, but it's not a dramatic cost increase. So this sort of showed us that there are options to reduce the water usage in plants that are use cooling water for its cooling purposes. If you replace the PCC plant or use air cooling for the PCC plant, it comes at an extra cost, but it's not extreme additional cost. As a next part of our study, and it's in the next slide, we looked at, we tried to integrate at options. We looked at options where we could use the produced water from a CO2 storage facility for cooling purposes in a power plant. And this is quite a busy slide, but it shows you 5 different locations. The top one, the Netherlands, is the case that I already presented. The bottom one is a similar case, but that one is in India, where you have different environmental conditions and also in each of these different countries, we use the local coal to operate the power plant, and it also defined the performance of the cooling system in the same time. The three countries in the middle, South of Africa, Australia, and China, were all based on the power plants were based, and these are all coal-fired power stations, on cases where the power plant was air cooled. There's simply no water available to operate the power plant. But we looked at the option that we added a capture plant, but that capture plant would then be operated, or the cooling system of the capture plant would be operated by evaporative cooling. And that can only be made possible if you can use the formation water. And on the right-hand side of this slide, you see the formation water that was available on these at these local points, and you can see quite a wide variation in terms of the salinity or the total dissolved solids of the produced water, ranging from 5,000 ppm in Australia and China, which is brackish water, to 150,000 ppm in the Netherlands, which is far more than seawater. So quite a wide range of salinities, and also quite a wide range of different conditions, which made it quite difficult to compare the various cases. You can see that the efficiencies that we ended up with for the power plants with 90% capture varied quite a bit, and the trends are there that if you have a coal that has a high ash content, that will also have a lower efficiency. If you have climatic conditions which are humid or which are high in temperature, that also means that you have a lower efficiency. And that's one of the reasons why for Australia we ended up with a fairly low efficiency. And for the Chinese conditions, they were the efficiency was quite high, and that was to do with the fact that we had quite cold conditions, and the cooling worked much more efficiently under those conditions, obviously. As I said, this is quite a busy slide, and I'll now hand over to Regina to discuss more the options of the integration of the power plant with the formation water production.
Thank you, Paul. Thank you. Yes, I just want to point out the storage basins that we selected or identified for the study, which was based on the storage capacity of around 4 million tons of CO2 per year to be injected over 25 years, or 4 million tons per year over 25 years. So around 100 million tons in total. And all these storage basins are located onshore, as we expected this to be a more realistic option when you do want to extract formation water and reuse it. I'd also like to point out that at the power stations in South Africa, China, and India, zero liquid discharge is a requirement. So it means the wastewater is treated and nothing should be discharged. So we apply this regulation also to the formation water treatment, so that to be consistent in the assumptions. So to assess the incremental cost of extracting and using formation water in the power station with capture, we compare the CCS base case scenario and the CCS-Water-Nexus. So we have the CCS base case sitting in the gray box here, and it's the USCPC power station using either evaporative or air cooling with a gross output of about 900 megawatts, and the capture plant using evaporative cooling at a capture rate of 90%. The CO2 is transported and stored in a saline formation located onshore at a rate of around 4 million tons per year. So this is our base case, or normal CCS. For the CCS-Water-Nexus, the CCS base case is expanded to include water extraction for the purpose of accommodating the CO2 safely underground. and the extracted water is treated to a target concentration of 100 milligrams per liter of total dissolved solid. So it's freshwater quality that could be used in a multitude of applications. The extracted water is around 7 million tons per year, which is based on the volumetric equivalent to the CO2 injected underground. So it's a ratio of about 1 to 1.7, depending on pressures. The technology used to treat the formation water depends on the salinity as well as the regulations. Do you have to treat to zero liquid discharge, or can you just dispose of the wastewater, the reject stream? The treated water is then supplied back to the power station with capture and used there, replacing other fresh water. If there's any surplus water, it could be it's maybe available for other beneficial uses. In addition to the assumption that was already shown previously on for the first case study, we have now differences in, well, we have the different coals, so we also have differences in cost for the coals. So India uses local coal, which is the cheapest at €1 per gigajoule, whereas in the Netherlands, coal has the highest cost at €2.5 per gigajoule. For CO2 transport and storage, we assume a flat rate of €5 per ton of CO2 stored, and for formation water extraction and transport, we assume a flat rate of €2.5 per ton of CO2 stored. This is also based on an economic assessment that was part of the study. And we assume, as pointed out previously, that the formation water is treated to freshwater quality with a TDS of 100 milligrams per liter. And here we have the water balance of the different USCPCs with capture. And so on the y-axis, we have water in million tons per year. We have South Africa, Australia, China, which use air cooling for the power plant. And on the right, we have Netherlands and India, which use evaporative cooling for the power plant, with all capture plants using evaporative cooling, which becomes quite obvious also if you look at the total water consumption and compare the air-cooled power stations and the evaporatively cooled power stations. The total consumption is in blue. The consumption for the capture plant alone is in orange. And again, you can see that for the air-cooled power station with capture, most of the water goes towards capture, whereas for the evaporatively cooled power stations, the capture plant only takes a comparatively small fraction of the total water consumption. In gray, we have the process water discharge, which in the countries where zero liquid discharge is a regulation, South Africa, China, and India, 90% of the wastewater is assumed to be recoverable. And so this is reflected in the yellow bar at South Africa, China, and India. So in Australia and the Netherlands, no water is recovered at the power station directly. And here we have the water balance for CO2 storage with water extraction. So I pointed out previously that the water extraction rate is around 7 million tons per year for the volumetric equivalent ratio from CO2 to water. Again, water in million tons per year on the y-axis. So you can see the gray bar is the water extraction rate for the different countries, the different locations, which are around 7 million tons. Plus minus for the different cases. And in blue, we have the product water that is the treated formation water. And you can see we get a bit more of a range in recovery there, which is a function of the salinity as well as local regulations. So for example, in Australia and China, we have low salinities, both of 5,000 milligrams per liter. But in Australia, we only have a recovery of 85%, whereas in China, we have a recovery of 99% because an additional treatment step is applied to get to zero liquid discharge. In the Netherlands, we have the extreme case of the ultra high salinity of 150,000 milligrams per liter. for which the recovery then is comparatively low at 25%. So you can see that with increasing salinity, the recovery decreases even where there's zero liquid discharge. So this is the water balance for the CCS-Water-Nexus scenario. So the total product water is in yellow. This is the water that is recovered at the power station where ZLD is applied and wastewater is treated and recovered, and the recovered formation water. In blue, we have the demand of the coal-fired power station with capture. So the air-cooled power station with the evaporative cooled power station in South Africa, Australia, and China, and the evaporatively cooled power stations with capture in the Netherlands and India with significantly higher water demand. And then in green, we have the difference between the water recovered along the CCS chain and the water demand of the power stations. So this can either be a surplus or a deficit. And in most cases, bar one, we do a surplus is achieved, also maybe recovered along the CCS chain, whereas in the Netherlands, due to the very low recovery from the ultra-high formation water and the high water demand of the evaporatively cooled power station with capture, there's a water deficit, and we would require just normal freshwater or water abstraction. So what does it mean with respect to the cost? So here we have the levelized cost of electricity in euro per megawatt hour. We have the capture plant, sorry, the power station without capture in the dark color. We have the CCS scenario, that's the middle bar. And then we have the CCS-Water-Nexus scenario, which is the lighter color. On the left, we have the air-cooled power station with capture, and on the right, so Netherlands and India, we have the evaporatively cooled power station with capture. And you can see easily by comparing the same power stations, we see that the LCOE vary quite a lot with location and range from 67 euro per megawatt hour in China for the base case up to 96 euro per megawatt hour in South Africa. And that's a result of the different conditions, efficiencies, ambient temperature, the salinities, I know that's in the next step, local costs, this is labor cost, construction costs, equipment costs. Water extraction, transport, and treatment in the CCS-Water-Nexus scenario can add up to another 3 to 7 euro per megawatt hour. In China, India, Australia, and South Africa, that's about 5% increase. In the Netherlands, that's an 8% increase. So in the Netherlands, the LCOE increased by the highest amount because the salinity of the formation water is very high, so recovery is low, and the disposal of the reject stream was quite expensive. And here we have the avoidance costs for the CCS base case and the CCS-Water-Nexus scenario. The CCS base case in darker blue and the Nexus scenario in light blue. Again, the air-cooled power stations on the left and the evaporatively cooled power stations on the right. Now you can see that the avoidance costs range from 36 up to 51 euro per ton of CO2 avoided in the base case. Again, the cheapest or lowest avoidance cost in China and the highest avoidance cost in South Africa. And if we add treatment or extraction, transport, and treatment of the formation water for the use in the power station, that adds another 5 to 11 euro per ton of CO2 avoided, which corresponds to 14 to 27% to the cost of CO2 avoided in comparison to the base case. Again, quite significant effect of location on the economics of CCS. I would just like to briefly outline some of the conditions encouraging the use of formation water. As we showed in this report or in this study, a big factor is the salinity, which should be sufficiently low to enable cost-competitive treatment. Likewise, high wastewater and brine disposal costs make treatment more attractive, or treatment might be cheaper than actually disposal, especially when it's costly transport and re-injection, and space is limited. When there is existing transport infrastructure for the water, or the extraction site and the point of use are co-located, or where there's already regulations that encourage water recovery or prevent wastewater disposal, such as the ZLD regulations at the power stations in China, India, and South Africa. Another factor is water reuse programs that may already be established. For example, in Australia, in the Strait Basin, co-produced water from coalbed methane fields is treated and used in a power station for evaporative cooling, and also used in irrigation schemes. Another factor is where water shortages reside in significant financial losses, for example, due to power station shutdowns, and this has been reported for India. So I'd just like to finish with the conclusions. These are the conclusions, one for the case study that Paul presented. As Paul showed, that the water consumption in power plants with and without CO2 capture depends on the cooling system, and air cooling at the capture plant reduces the overall water consumption compared to the same power station without capture when the power station uses evaporative cooling. This reduction in water consumption comes at a cost, of course. If you compare the whole power station, the evaporatively cooled power station with capture, and an air-cooled power station with capture, the LCOE for the air-cooled power plant with capture are 9.4% and 7.7% higher for the air-cooled power plant than for the evaporatively cooled USCPC and NGCC, respectively. We only look at the capture plant for an evaporatively cooled power station. The LCOE for the air-cooled capture plant are 5.3% and 5.4% higher for the air-cooled power plant at the USCPC and the NGCC, respectively. And here are the conclusions for the second case study, which showed that the local conditions can significantly affect power station water consumption and costs because of factors such as climate, feedstock, regulations, local costs, and environment conditions such as the formation water salinity. Water extraction, transport, and treatment is estimated to add 5 to 8% to the LCOE in our study, which corresponds to 3 to 7 euro per megawatt hour, and can add 5 to 11 euro per ton in avoidance cost. We also found that water recovery along the CCS chain may result in a surplus exceeding the demand of the power station with capture. Again, this is very case specific, depending on the demand of the power station, the quality of the formation water, and also local regulations. So how much water will be recovered from the formation water and how much water is recovered at the power station, if any. And just want to conclude with that the recovered water may provide a valuable unconventional resource in regions where water stress is causing significant financial losses, with product water costs comparable to local water tariffs. This does not include the cost of water extraction and transport in this case. And that's it. Thank you very much.
Okay, thank you very much, Regina. Thank you, Paul, and thank you, Monica. So we have a few minutes, literally just 5 minutes for questions now. We have a question in which you haven't considered, but the question was, have you considered utilization of CO2 as a refrigerant to cool the systems? I think you didn't cover this, but maybe you have some thoughts on the use of CO2 as a refrigerant for cooling instead? Paul or Regina?
I'll pass it on to Paul. Are you on mute?
Microphone, yeah.
Okay. Well, thanks for the question. We didn't look at CO2, the use of CO2 as a refrigerant. My initial reaction to that would be that to make the CO2 available as a refrigerant, you need to have it at in a compressed state. Of course, we're going to compress it for CO2 storage, but that comes with an energy requirement. So I'm not sure whether it would be beneficial to find any use of CO2 for refrigeration processes or for cooling in any way. But that I haven't come across a system that could do that energy free. But interesting to learn more about any of these options.
Okay, thank you, Paul. So another question. So in your assumptions, you've used the 90% capture rate. Is there any significant impact if you increase the capture rate? And as you know, we can go up to 99.7% capture rate, thanks to your previous work, Paul and your colleagues there. But is there any impact if we do go up to these higher capture rates?
I think that would certainly be possible. Just have to mention that our previous study was based on MEA. We're now using a different system that is more energy efficient, but I don't see a major obstacle there. What we found in our previous study is that if you want to go to high capture rates, you really have to design for high capture rates. So that's an important was an important finding. Higher capture rates do lead to higher costs and a higher reboiler duty for the capture system, so for the regeneration of the absorption liquids, and that inevitably will also lead to some higher water demand. In our previous studies, we found that those increases were not terminal, and I think that would certainly be an option that would be worthwhile to pursue.
Okay, thank you, Paul. And another question, China seems to be favorable in terms of costs. Could you explain a bit further the reasons for this positive scenario?
Yes, it's basically China had the lowest capital cost, operating cost, and fuel cost. And yeah, it's mostly the labor cost, equipment cost. The ambient conditions were also favorable. And I'm pretty sure they had the power station at the highest efficiency, and so that resulted. There's a lot of factors playing into this, and but yeah, these are the predominant factors which made China, the China location, more beneficial than over the others.
Okay, thank you. And then a question for Monica. What are the next steps for IEAGHG's area of study here?
Yeah, did you hear me well now? Yeah?
Yeah.
Yep. Okay, yeah. Yeah, because I was having some problems. So maybe next steps that we have concluded from this study will be to explore all the CO2 capture systems. So we have explored in that one post-combustion system based on chemical solvents. So maybe to explore all the options that could have a different water requirement. So that could be also one of the lines to explore further. And also we have in all our studies we are including more detailed information about the assumptions and limitations. So maybe we can explore further some of the assumptions and limitations or methodology, let's say. So that could be also another pathway to go forward.
Okay, thanks, Monica. Okay, well, we're just about up on time now. So thank you very much, Paul and Regina and Monica, for your presentations. I think it's very interesting to see, this is the first time we've looked at the costs of reducing water. It's good to know that there are means of reducing water consumption for the capture plants, and you've included the power plant as well. And the costs, are not unreasonable, I would suggest, when you look at the IPCC's modelling, or the modelling that they used to the end of the century for mitigation costs in the hundreds to thousands of dollars per tonne of CO2. They still put CCS at the low cost end of the mitigation options, and with zero liquid discharges as well included. So thank you very much for that really good work, Paul and Regina, and thank you very much, Monica, for the review of the previous work and the background and the context. And thank you very much to all the attendees listening live, and to those who will listen to the recording of this as well. I hope you all are keeping safe and well. And thank you very much to Suzanne at IEAGHG for facilitating the webinar as well. So with that, thank you very much and goodbye.
Okay. Thank you.
Thank you.